welcome to Mr. Saucedo's YouTube videos. Today we're going to be going over Chapter 16 in Zumdahl, the 7th edition. It's all about spontaneity, entropy, and free energy. So, Section 16.1, all about thermodynamics versus kinetics. So, we haven't covered kinetics yet, but something that you need to recognize is that thermodynamics is really focusing on just how a reaction starts and how a reaction ends. So reactants and products. It's kind of what we talked about in section, I don't remember what section it was, but it was chapter 6. So these are what we call state functions, right? Where you only really need to know what energy you ended up with and what energy you started at. It doesn't matter the pathway that it took to get you to, from A to B. So kinetics, though, is really interested in the amount of time it takes for a reaction to occur. And so what we're looking at is really the pathway itself. So kinetics is always going to be situated with the rate of the reaction, and specifically how you get from point A to point B. Thermodynamics, though, only tells us whether or not a reaction is spontaneous, which means, does this reaction happen or does this reaction not happen? And so, again, it's only based on the properties of the reactants and products. So we only care about the end point and the starting point. That's it. So something important to kind of recognize here is that thermodynamics does let us predict the direction in which a process will occur, but it doesn't give us information about how quickly that reaction will occur. So for example, spontaneous processes can happen very quickly or very slowly. But all we know is that if a process is spontaneous, that means that it is a reaction that will happen without any outside intervention. You do not have to do a single thing to it in order to get it to happen. So a good example of that would be like rust. Rust is a spontaneous chemical reaction that will happen to iron, no matter what you do. Okay, if we leave iron out, it's going to slowly oxidize, but it takes a really long time. So kinetics would be kind of the field where we'd figure out, okay, how quickly does this reaction occur? With spontaneity and thermodynamics, all we'd really be able to tell you is that this is a spontaneous process that happens without any outside intervention. So here's a good example of a good concept check. So we have 2.4 moles of gas contained in a 4.0 liter bulb at a constant temperature, 32 degrees Celsius. This bulb is connected to a valve and is connected by a valve, to an evacuated 20-liter bulb. Assume the temperature is constant. What should happen when I open the valve? Just think about it. What should happen? So again, thermodynamics is telling us that it doesn't matter, again, the pathway that we took, but what should happen is the gas should spread out so that it totally fills both of the bulbs up. And so the whole point of this is that it happens spontaneously. I did not have to add any energy to this system in order to get those gas molecules to move from one bulb to the next and then bounce around and keep going between both of the bulbs. And so spontaneity is one of the big focuses of what we're going to be talking about today. And so now let's think about the stuff that we learned from chapter 6. So let's remember enthalpy, energy, and then heat. So if I give you the exact same situation, what do you think the delta H, the delta E, and the Q is going to be for the following, situation, the same situation as on the previous slide? So I'm going to tell you the logic here. But let's start. First of all, Q is 0 at a constant temperature, right? So heat is constant in this situation at 32 degrees Celsius, which means that there's no heat transfer occurring in this situation. Now remember, we had a lot of equations, but another good equation was that at a constant pressure, delta H is equal to Q. And we do have constant pressure in this situation. And then finally, delta E is equal to Q plus W. And there's no work being done because we had an evacuated container that this is going into, so there's no work. So in reality, all of these things are zero. The heat, zero. Enthalpy change, zero. Internal energy, zero. So now the question becomes, what do you think the driving force is for this process? We all know that the gas is going to spread out and fill up the evacuated bulb, but what is causing it to do so? The answer is entropy. And yeah, I know it's kind of weird. Entropy is abbreviated as capital S. But now let's talk about entropy, okay? So again, we know what's going to happen when we, open up this valve. It's going to spread out until everything is equal. Now, why and how does entropy work? Okay, so entropy, what is entropy? So in general, this is not like the chemistry definition stuff, okay? So this is just how people describe entropy. So entropy is the driving force for spontaneous processes. And so a spontaneous process will lead to an increase in the entropy of the universe. And so when we say entropy, what we're thinking of is normally molecular randomness or disorder. So in other words, you're thinking of the fact that the ideal state, let's say, of a brick wall would be that brick wall broken down into pieces. And so disorder is what people think about when they think of entropy. Now, again, if I were to give you two of these and say, okay, I have ice cubes and I have a cup of water, which one of these situations has more entropy? Most people would pick the water. Why? Well, a solid like this is more ordered, right? You can picture that in this crystal, we have water molecules that are all being held together by hydrogen bonding. And, they're just basically kind of stuck in one place and they're vibrating a little bit. Whereas here, the water molecules are free to flow. They're free to move around. They're still stuck together, but they're not as stuck together as in this situation. And in fact, yes, liquid water has more entropy than solid ice would. So even intuitively, entropy-wise, a lot of people can kind of make some determinations, but what does it mean chemistry-wise? So thermodynamically, what is entropy? So it is a thermodynamic function that describes the number of arrangements that are available to a system existing in a given state. So yeah, randomness and disorder are great terms to kind of picture, but especially in AP, and on the AP exam, they don't want you to use the term disorder to describe entropy. Instead, they want you to think about the arrangements that a system has. And specifically, they call them microstates. But the whole point of entropy is that nature spontaneously proceeds towards the states that have the highest probabilities of existing. So entropy is really about probability. And so the greater the probability that a particular item or a particular substance exists in that state is going to have more entropy than if there is a lower chance, a lower probability of it existing in that state. So I like to think about it like this, like Connect 4. So if you were to play, a bunch of games of Connect 4, what are the odds of you having, again, let's say you don't stop. No, there's no winner here. You're just going to add a red little puck, or you're going to add a yellow puck. So let's say you just spontaneously or randomly adding them. What are the odds of you getting a complete column of yellow, a complete column of red, a complete column of yellow, and it alternates like that? The odds are pretty slim. And so that would be, again, a very low probability state of existence. But, if we're doing this randomly, if I said, what are the odds of there being about, half of each of these columns has, a red little puck, and the other half have kind of like, the odds of there being like, a yellow puck instead. So instead now of looking at like, a perfect pattern, now we're looking at, more of a random chance. The probability is much higher in that situation that you're not going to have these nice, neat rows. And so that's really what entropy is about. It's all the possibilities. So if I were looking at Connect 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7. So it's a 7 by 6 square. These are the different possibilities that I can have, and Again, it's all about probability. So what they do want you to say, though, like I said, is not really the word disorder, but they want you to talk about microstates. So let's say I have 4 molecules in, this kind of same apparatus we saw earlier. So I have 2 bulbs. What are the odds of all 4 of them being in one side? Well, there's only one arrangement where that can happen. And I've labeled all of these molecules A, B, C, and D. Same thing. There are 4 different arrangements that will get me 3 molecules and 1 molecule. There are 6 arrangements that give me 2 molecules and 2 molecules. There are 4 arrangements that give me 1 molecule and 3, and then there's one situation where I could have 0 on this side and 1 on this side. So clearly, the most probability, or the highest probability, would be for this situation to happen, which is, again, what we assume when we talk about diffusion happens. So it isn't that this is impossible, and it isn't that this is impossible. It's just that these microstates are not as likely to occur. Let's talk about positional entropy. So positional entropy is, again, kind of what we've been talking about, but let's say we have this situation. A gas expands into a vacuum to give a uniform distribution because the expanded state has the highest positional probability of states available to that system. So again, we're looking at position. So now this explains why solid ice, liquid water versus steam, why we have more entropy. In a solid, there are fewer states. There are fewer microstates. In a liquid, there are more microstates. There's more freedom. In a gas, there are many more microstates that are available for these gas molecules to exist in. So this is the reason why solids have low entropy and gases have high entropy. Again, picture this. You're all stuck together. Here we have more freedom. Here we have a crazy amount of freedom. All right, now let's talk about the sign of delta S here. So the sign is important. Remember, S stands for entropy. So if delta S is positive, that means that entropy is going up. If delta S is negative, that means that entropy is decreasing. So let's actually look at this. The evaporation of alcohol. So picture that, right? I've got alcohol in the bottom of a container and it is evaporating. Positive or negative? Answer, positive, right? Entropy is increasing. There are more microstates available to alcohol in the gas form than there is alcohol in the liquid form. What about freezing water? You guessed it, there are less microstates available to solid ice as there is liquid water, compressing an ideal gas at a constant temperature. Again, we're making this more ordered, right? So there, again, you don't want to use the word order though or disorder when you're explaining this on like the AP test. So we want to use microstates. So when I'm compressing an ideal gas at a constant temperature, there are less microstates available for it to be able to do what it needs to do. Heating an ideal gas at a constant at a constant pressure. How would you heat it up then, huh? So the answer, positive, right? If you're increasing the heat, that means that now there are more microstates available because you have more energy. And now dissolving NaCl in water. When I dissolve NaCl in water, what do I see happen? You guessed it. I have more randomness available because now instead of this being in a crystal, it now has the ability for these positive and negative ions to float around. All right, so let's talk about the second law of thermodynamics. So first law we already talked about. That was the law of conservation of matter, and that was in, chapter 6. So second law, in any spontaneous process, there is always an increase in the entropy of the universe. So in other words, the entropy of the universe is always going to be increasing. So again, to try to connect this to the first law, just to make sure that we understand what the second law really is saying, total energy of the universe is constant. That was the first law, right? Law of conservation of energy. But that does mean that still entropy is increasing. And so if we're looking at a very simplified version, let's say, of entropy here, and we're looking at the entropy of the universe, that's always going to be equal to the entropy of the system plus the entropy of the surroundings. So that should look very familiar to those of you that have already seen the video on chapter 6. It's literally like we just replaced enthalpy with entropy here. But as a little bonus, for spontaneous processes, the entropy of the universe is always going to be greater than 0. Now, let's utilize some of this information. So when we say the change in entropy of the surroundings, if it's positive, that means the entropy of the universe increases. If it's negative, the process is spontaneous, but only in the opposite direction. And then if it's equal to 0, that means that the process has no tendency to occur at all. All right, so let's take a look at a concept check. So for the process, let's say we have liquid element A, and we're turning that into solid element A. Which direction involves an increase in energy randomness? So we're looking really at like enthalpy here, and positional randomness. So we're looking at entropy in that situation. So let's see if we can figure out what's going on in that situation. So first thing that I would look at is, okay, what is happening with energy on both sides of this double arrow? So on the left side, right, I have a liquid, and then on the right side, I have a solid. Great. What has to happen to turn a liquid into a solid? Energy has to be released. So that means that this process is an exothermic process. So like it says, the process as written is exothermic. And so energy randomness will favor, exothermic reactions. So we have our solid on this side. And so that would be what is favored in this reaction. But looking at entropy, so looking at positional randomness now, so microstates, liquids have less order than solids do. So that means that if we're looking from an entropy standpoint, that this side would be the favored part. I would really want the liquid more than I would want the solid if I'm looking at higher entropy. So now, what happens if I change the temperature? What if I increase or decrease the temperature? Which one wins out? Is it the energy part or is it the entropy part? Which part does? So as temperature increases, positional randomness is favored. That's entropy. And the reason why is because, again, at high temperatures, it doesn't matter really how much energy is being released. That doesn't become very important because entropy is going to be increasing if temperature goes up. Now, if temperature is decreasing, then that energy becomes very, very important because now exothermic processes, like in that situation, if we decrease the temperature of an exothermic process, it's going to make it less likely, but it's also going to make the reaction want to generate more heat. So now let's think, at what temperature would there be a balance between both entropy and enthalpy? So where would that really occur? And so that would occur at the melting or boiling points, because at that point is where we switch, right? That's the point at which we now switch from a liquid to a solid, or a solid to a liquid, or a liquid to a gas, or a gas to a liquid. So it's really at these points where there is a perfect balance between the two. Now, what's the point of me actually telling you this? I promise we'll get there soon, but concept check again. Let's use intuition here and what we know already to try to figure this out. So let's say I have an exothermic reaction and it's increasing in entropy. Do you think that process is spontaneous, not spontaneous, or can we not tell? Answer: it's spontaneous. Exothermic reactions that increase the entropy of the reaction, those are always going to be spontaneous. What about an exothermic reaction that is going to lower the amount of entropy? That we can't really tell. More on why in a second. What if it's endothermic? So if it's endothermic and it's going to make more entropy, we still can't really tell under those circumstances. And then for an endothermic process that is going to be making something have less entropy, that's going to be not spontaneous at all. So we have two hard ones that we know 100% of the time. If it's exothermic and it's increasing the entropy, it's going to be spontaneous no matter what. If it's endothermic and it is not going to be increasing entropy but decreasing it, it's not going to be spontaneous. And then for the other two situations, we can't really tell. And here is how temperature affects our answers. So for the first one, it doesn't matter. The temperature can be anything. Both driving forces are favorable, the energy part, the entropy part. And so, for example, combustion of methane, setting something on fire, that's going to be, again, a spontaneous reaction in that situation. Exothermic, though, and making something become less positionally random, so we're making it more ordered, in other words, right? The microstates are decreasing in amount. That really depends on the temperature. So a good example of that would be freezing water. So freezing water is an exothermic reaction, or an exothermic process, I guess I should say, sorry. And it's making something more ordered, because now we are, turning something from a liquid to a solid. So it really depends on the temperature. If the temperature is, 0 degrees Celsius or lower, it's spontaneous. But if you go above 0 degrees, it's not spontaneous anymore. So you can see that it really depends on the temperature you're at. Endothermic reactions that are making things more disordered, though. So a good example of that would be, again, vaporizing water. In order to boil water or vaporize water, you have to put energy in. So it's endothermic, it's absorbing that energy. And it's making something more random, though. You're going from a liquid to a gas. And again, it depends, go figure, on the temperature, right? At 100 degrees Celsius, it's going to be spontaneous. Above 100 degrees Celsius, it's going to be spontaneous. But below 100 degrees Celsius, it's not spontaneous at that point. And so last but not least, an endothermic reaction becoming less positionally random, both of those are unfavorable things. And so the answer to that is, it's not going to happen. So why am I telling you all of this? Well, that's because when we're looking at delta S of the surroundings, the sign, whether it's negative or positive, is telling us something about the direction of the heat flow. How big of a number we get is telling you information about the temperature itself. And so, again, the driving force, if provided by the energy flow, is going to be directly related to the magnitude of the entropy that we see in the surroundings. And so the way that we actually measure entropy, so if you're wondering what units do we use, we need to look at temperature and we need to look at the quantity of heat. So in reality, entropy, S, is measured in joules per Kelvin. And that's because we're interested in the heat, which is, the driving force, and we're interested in what temperature, so that we can tell whether or not it's going to be spontaneous or not. All right, so for an exothermic process, delta S is going to be a positive value. For an endothermic process, delta S is going to be a negative value. And so again, we're looking at joules per degree Kelvin. And so it's important to recognize that when we have an exothermic process, this is what's going on. When we have an endothermic process, this is what's going on. And again, we're looking at the delta S of the surroundings. So Q is equal to the change in enthalpy at a constant pressure. That's something from chapter 6. And so the nice thing is that we can take a look at what delta S of the surroundings really is looking at, and that's equal to the negative, so that's where the negative part comes from, delta H over T. And so remember that all of the situations we're going to be looking at are always at constant pressure anyway in these types of situations. So that's why we kind of have to say, by the way, Q is really equal to this. So instead of Q over, T, we really like it to be delta H over T. And this little negative sign here is, again, keeping track of the sign that we just talked about on the previous slide. So here's kind of how this works. If the delta S of the system that we're looking at and the delta S of the surroundings is positive, the delta S of the universe is increasing and the spontaneous process occurs. On the other hand, if it's negative and negative, then it's not going to occur. And then it depends. if delta S is positive and, of the system, and delta S of the surroundings is negative, it just depends on how big these numbers are. So like it says, is the process spontaneous? Yes, if delta S of the system has a larger magnitude than the delta S of the surroundings. On the other hand, if they're flipped, again, yes, it's spontaneous, but only under particular conditions. If delta S of the surroundings has a larger magnitude than delta S of the system. So again, when you're trying to figure out if something is spontaneous, these are the kinds of things that we need to look at. And now the last bit, so the little cherry on top for thermodynamics is free energy. And so it's Gibbs free energy, and it's identified as a capital G. So chapter 6 was all about enthalpy, which was H. The first part of this was all about entropy, which is S. And the last part of this is about free energy, or Gibbs free energy, which is G. So these are the three big thermodynamic quantities that even in the appendices of your book, you have a bunch of tables that have all three of those values for any substance you can possibly think of. So here's another little connection, let's say, between these two. So the delta S of the universe, so now we're looking at, overall entropy in the universe. That's going to be equal to the change in free energy over temperature. And again, the negative sign here is keeping track of what positive and negative really mean when we're looking at this overall. So delta G, though, is the change in Gibbs free energy. And so a process at constant T and P, because again, we're making sure that we're not saying that T is changing, because it can't, right? It has to be a number specifically. And P can't change because then we have work, and that's just a big old mess. It's going to be spontaneous in the direction that free energy will be decreasing. So in other words, negative delta G means positive entropy. So spontaneity is really what delta G is getting at, whether something is spontaneous or not. If we see a negative delta G, that means that that process is spontaneous at that temperature. On the other hand, if delta G is not negative, so if it's positive, that means that entropy is going down. That means that the process is not spontaneous. It's not going to just happen without outside intervention at that temperature. And so the connection, the big connecting force between all of the things we've been talking about is this formula. Delta G is equal to delta H minus the temperature times delta S. So the change in Gibbs is equal to the change in enthalpy minus the temperature at which we're looking at this reaction occurring times the change in entropy for that reaction. And so here's a good kind of example here. The value of delta H of vaporization of a substance, whatever the substance is, it doesn't matter. So substance X is 45.7 kilojoules per mole at its normal boiling point, and it is at 72.5 degrees Celsius. So what is delta S and delta G for 1 mole of this substance at that particular temperature? And it's telling us that, the pressure is constant here, because we have 1 atmosphere. So let's use this. Delta G equals delta H minus T times delta S. And so you might think, okay, I'll plug in these numbers, right? Okay, so great, that's H. I converted this to Kelvin, and so that's there. And you might say, great, I have 2 variables. I can't solve for these both. And you're right, you can't. So remember that the magic point is at boiling point or the melting point. And so that would be not just, that would be the point at which, believe it or not, delta G is equal to 0. And you might think, okay, why is delta G equal to 0 at the boiling point? Think about it. It's what we just talked about. At the boiling point, that is the point at which things switch. So if I'm looking at this from one perspective, I'm going from, let's say gas to liquid at that point. But I'm also going from liquid to gas at that point. So that is the transition point, right? That is the point at which Gibbs free energy is equal to 0. And the reason why is what I just said. At that exact temperature is going to be the point at which things become either spontaneous or not spontaneous. So is it spontaneous at this point? It depends on your perspective. It depends on whether we are looking at moving from 72.5 degrees Celsius to 72.6, Or are we going from 72.5 degrees Celsius to 72.4? Because depending on which direction we're moving, that's going to affect what's actually going on here. So it makes it, though, easy for us to plug in now 0 here, and now we can find the entropy. So let's find the entropy. All right, let's solve. So delta S is equal to this side, so I moved it over, divided by this. I'm not putting any units in just so that, you can kind of, there are units though, right? But let's say that I'm not putting in units just so that it's a little bit cleaner looking. But when I put that into my calculator, what I get is 0.132, and now I'm going to put the units in. Negative 45.7, that's in kilojoules per mole, okay, so I still have that. And then this temperature is now in Kelvin, so Kelvin would go down here, so it would be 0.132 kilojoules per Kelvin mole. Now, here's the thing about entropy. It's almost always going to be looked in your book and measured in your book in joules, not in kilojoules. So I'm going to convert that to joules instead per Kelvin mole. And so it's 132 joules per Kelvin mole. And so that's how I would utilize this equation to solve for that. Another good one, though, would be if they gave you information about Gibbs free energy and enthalpy and entropy, and they're asking you for a temperature. That would be a really good one too, because then you could find what temperature are we talking about? Or even better, I should have done this as an example. That would have actually been really cool. But at what temperature does something become spontaneous? Because then delta G would be 0, because that, again, is like the shifting point, whether something becomes spontaneous or not. And so if you had delta H and you had delta S, you could find the temperature at which that occurred. What temperature did it become spontaneous, which is kind of nice. So let's talk about the effect of delta H and delta S on spontaneity. So again, here's a good summary table. We've got delta S if it's positive and delta H if it's negative. It's spontaneous at all temperatures. If delta S is positive and delta H is positive, then it's spontaneous at high temperatures. Because again, if it's at high temperature, the exothermic part of that doesn't really matter. Delta S is negative and delta H is negative. That's going to be spontaneous at low temperatures, and that's because, again, now exothermic reactions become extremely important, right, where that's the dominant part that we're looking at. And then delta S negative, delta H positive, the process is not spontaneous at any temperature. It's never going to be spontaneous at all. And so the third law of thermodynamics, we've done the first, the second, we might as well talk about the third. It's the last law of thermo. Entropy of a perfect crystal at 0 degrees Kelvin is defined as 0. And the entropy of a substance increases with temperature then. So you can picture absolute 0 as being like the 0 point, let's say, for entropy. And then every time you increase the temperature above absolute 0, you should have an increase in entropy as a result of that. Now, what about standard entropy values? So let's represent the increase in entropy that occurs, like it says, when you have a substance and it's heated from 0 to 298 Kelvin, which, by the way, is pretty close to room temperature, at 1 atmosphere of pressure. So guess what? It looks exactly like the enthalpy equation that we had in Unit 6. The delta S, so again, remember this little thing means it's in its standard state that we're looking at. We're looking at a state function here. Is equal to the sum of the number of moles times the entropy of all of your products minus the sum of the moles of all of your entropies of your reactants. And so we can do that. In fact, I think this is the exact same question we had before, just instead we're looking at entropy instead of looking at enthalpy. So if this looks familiar to you, it's because you probably watched the video on chapter 6 already. So we've got sodium, I've got my water in liquid form, I've got my sodium hydroxide, aqueous solution of it at least, and I've got my diatomic hydrogen gas, all right? So if you look up our entropy values in the back of the book, this is what we get. So let's actually do our nice little math here. All right, so I have 2 NaOHs, so I would double that, and I have 1 H2. So I would add those together. That would be my product side of the reaction already done. And then I'm going to subtract my 2 NAs. That would be right here because 1 NA is 51, so I have 2 of them. And then I would add together my 2 waters. So I have 2 70s. And so when I subtract the products from the reactants, I get negative 11 joules per Kelvin. And that would be the entropy for this reaction. All right, so standard free change of energy. So again, delta G, guess what? We can do the exact same thing with delta G. Absolutely fantastic, yay. So just remember that delta G is equal to delta H minus the temperature times delta S, right? And so the nice thing is that because of this, because we can do state function stuff again, we can do the exact same thing we did with entropy. So guess what? You can do it with enthalpy, you can do it with entropy, you can do it with Gibbs free energy. And so again, that's why the table in the back of your book also has Gibbs free energy information for every substance, because we can do the exact same subtraction. So take the sum of the number of moles of your products minus the sum of the number of moles of your reactants, and there you go. You get your change in Gibbs free energy for your reaction. And so let's just, instead of doing another example that's exactly the same as ones we did in chapter 6 and also just on the previous slide, let's try to see if we can do this conceptually, because it's going to be a lot more hopefully obvious now what's going on. A stable diatomic molecule spontaneously forms from its atoms. What do we think the delta H would be? So positive or negative, or the delta S, or the delta G, and let's explain. So the first thing that I notice is that it says that we've got a spontaneous reaction. So if delta G is negative, that means that it's spontaneous. Okay, great. Next thing that I would look at delta H. So for delta H, a stable diatomic molecule spontaneously forms from its atoms. So let's picture two hydrogens, and they're being put together to make a hydrogen, a diatomic hydrogen, so two hydrogens bonded together. Now, remember, bond forming is exothermic. That means that delta H would have to be negative. Because remember, exothermic is basically a negative delta H. And now last but not least, what about our entropy? So I'm going from two hydrogen atoms bouncing around to a hydrogen atom bonded to another hydrogen atom. That is more ordered. We now have reduced its microstates significantly. So in reality, entropy has actually decreased. So entropy is also a negative. So in reality, all of these end up being negative for different reasons. This is negative because it's spontaneous. This is negative because it's an exothermic process. And this is negative because it is making something more ordered. Okay. Now let's do a slightly harder example. Consider the following system in equilibrium. So I have PCl3, so I have phosphorus trichloride, plus diatomic chlorine, and then I'm making phosphorus pentachloride here. It's giving me a delta G value of negative 92.50 kg. What will happen to the ratio of partial pressures of PCl5 compared to the partial pressure of PCl3 if the temperature is raised? And right now, that probably looks like, what am I supposed to do? But we're going to piece everything together. So I'll tell you the answer first, though. The ratio will decrease, and now let's explain why. And so to do that, we're going to look at delta H for this, delta S, and delta G. And the first thing that I would notice is that this is becoming more ordered. This is more disorder, this is more order, but again, remember, they want us to use the word microstates. So this has less microstates than these do. Possible. So entropy would be a negative here in this situation. Here's another thing, though, that we need to look at, okay? Delta G is negative here. Negative, right? What about delta H? So we are combining together something. We are forming bonds, it looks like, right? So yeah, we're breaking a bond here, right? But we're also forming more bonds here. So that would mean that in order to do that, this would be an exothermic process. Because again, remember, bond formation is going to be an exothermic process. Bond breaking is an endothermic process. Okay? So all of these are negative. Now, how am I going to figure this out? Well, remember, we have an equation. Delta G is equal to delta H minus the temperature times delta S. So let's picture this. This is a negative number. This is a negative number. This is a negative number. the temperature becomes really important, right? Because whether or not this delta G is going to be positive or negative really depends on the temperature, how big this is versus this. Because this is negative and then it's subtracting and this is negative. So it really depends how big this is. So think about that. If I start to increase the temperature, so this number is getting bigger and bigger and bigger and bigger in magnitude now, eventually delta G is going to equal not a negative number anymore. And so that would mean that the ratio would decrease between this side and that side, because it would start being, it's more this favored now, but it's going to become less favored and start going the opposite direction afterwards. Now, free energy and pressure. All right, now this is just kind of like a last little equation thing, but so G is actually equal to, so this is the standard state function for G, plus R, which is the universal gas constant, times the temperature times the natural log of pressure. Another way of writing that, though, would be to look at the change in Gibbs free energy again. And this would be like our state function we can look up from our table in the back. Plus, again, same exact thing. And this is our reaction quotient. Okay, our reaction quotient, again, whether or not you know what that is yet, I'm not entirely sure. It just depends if you've already talked about equilibrium or not. So what does this mean, though? So that's just a little throwaway equation. If given information, you could easily, kind of figure out what's going on with that. So what's the meaning of G for a chemical reaction? It really is telling us the following. A system can achieve the lowest possible free energy by going to equilibrium. So you don't need to complete the reaction. You can totally reach equilibrium and be done. Okay, you don't need to go all the way. And so what this is kind of showing is like, it isn't just a ramp where you go from A to B and you're done. Let's say this is your equilibrium point. And so, you'll roll up and you'll roll back and you'll roll up and you'll roll back. And eventually you'll reach your equilibrium point after rolling back and forth a couple of times. And so that's really what free energy is all about. Okay. So the equilibrium point occurs at the lowest value of free energy available. And the lowest value, is going to be when it's equal to zero. Again, good old zero. And so in reality, if we rearrange our equation after setting this equal to zero, we get that delta G, so the state function of delta G here, is going to be equal to the negative R times T times the ln of K. Again, K being the equilibrium constant. So this is the last slide, but delta G, if it's equal to zero, that means your equilibrium constant is equal to zero. Or sorry, is equal to 1. It can't be equal to 0, sorry. If delta G, on the other hand, is less than 0, that means that K is going to be greater than 1. And if you have no idea what that means, it's probably because you haven't really done equilibrium yet. But that means that you have a product-favored reaction in that situation. Delta G, if it's greater than 0, that means that K is actually going to be less than 1, which means that you're going to have a reactant-favored reaction in that situation. And that is the end of chapter 16. So thanks for listening. And if you have any questions, please make sure to just email me or leave a comment. And so stay tuned for our next chapter. And thank you for liking and subscribing.